It is useful and often necessary for a surveyor or engineer to be able to calculate coordinates. Surveyors will often see coordinates in the form of x and y, or northing and easting. Northing is akin to the y coordinate and easting being akin to the x coordinate. To calculate coordinates, starting coordinates are required along with a direction and distance. Calculations are more easily done using an azimuth for the direction rather than a bearing. Using bearings, mistakes are often made because negative values must be identified and applied manually rather than resulting automatically from the calculations that occur while using azimuths. Most calculations require the direction be in degrees and decimal parts of a degree before using a trig function on your calculator, rather than degrees, minutes, and seconds that are the units typically displayed on surveying equipment. If an Excel spreadsheet is used, the angle value must be in radians. Many calculators have a function key that will convert degrees, minutes, and seconds into decimal parts of a degree. Sometimes this function on a calculator is displayed as a time conversion of hours, minutes, and seconds to hours, the conversion between time or angles being the same. The person practicing the profession of surveying or engineering will soon master the keystrokes on their calculator to accomplish this task. For those that do not have a function to convert degrees, minutes, and seconds to degrees and back on their calculator, or do not know how this function is accessed on their calculator, a manual conversion can be done by taking the minutes and dividing by 60. This is added to the seconds that are divided by 3600. That is then added to the degrees. Hence, an angle of 42 degrees, 50 minutes, 36 seconds is converted to decimal degrees by taking 50 divided by 60 and 36 divided by 3600 and adding both to 42 degrees to give an angle of 42.8433 degrees. Should it be necessary to convert this angle to radians in order to use the Excel spreadsheet, the value is divided by 180 degrees, then multiplied by pi. Calculating coordinates is based on right-angle trigonometry. As seen by the diagram, the change in the x direction is a function of the sine. Consequently, the change in x direction is equal to the sine of the azimuth times the distance. The value that results from this calculation is known as the departure. The departure is added to the previous x value to get the new x value. The equation can be written as shown. Again, referring to the diagram, the change in the y direction is a function of the cosine. Consequently, the change in y direction is equal to the cosine of the azimuth times the distance. This value is known as the latitude. The latitude is added to the previous y value to get the new y value. The equation can be written as shown. I have previously mentioned that using azimuth is much less prone to error than using bearings. Let's explore coordinate calculations using bearings. A northeast bearing is the same as using an azimuth. However, a southeast bearing requires that the change in y be given a negative value based on the convention that x values increase going from left to right and y values increase going from bottom to top. If an azimuth is used rather than a bearing, such as 135 degrees, cosine value of the azimuth will automatically result in a negative value. A southwest bearing requires the change in x and change in y both be negative. Yet, if an azimuth of, say, 200 degrees is put in the calculator and the sine and cosine values obtained, both will result in negative values without further thought. Finally, for a northwest bearing, the change in x must be made negative. While an azimuth in this quadrant, say 300 degrees, is placed in the calculator, the sine function automatically gives a negative value. Many choose to convert all bearings to azimuth before calculating coordinates. A separate video shows the calculation from a bearing to an azimuth. New surveyors will often ask why azimuths were not used for property descriptions rather than bearings. Having practiced surveying close to half a century, I remember doing calculations before calculators. In those long ago days, trig functions had to be obtained from published trig function tables. The trig function in the books were listed from 0 degrees to 90 degrees, hence bearings were best for looking up the trig functions. A practical demonstration of coordinate calculations can be done using the following deed description. A table is used to facilitate the computations. The column headings are corners, bearing, distance, azimuth, departure, latitude, x-coordinate and y-coordinate, beginning at a post, then south 43 1/2 degrees east, 345 feet to stones, then south 5 1/4 degrees west, 389 feet to a stone, thence north 68 degrees west, 450 feet to the road, thence along the road north 78 1/2 degrees east, 151 feet to a point, thence north 8 1/2 degrees east, 444 feet to the point of beginning. Starting coordinates must be assumed. In order to avoid negative numbers during calculations, the starting coordinates must be large enough to avoid negative numbers. Starting coordinates for the post corner are assumed to be x is equal to 2000 and y is equal to 2000. These are inserted into the table. Next, the azimuth are calculated from the bearings. The table that was developed under the topic is used to calculate azimuths from bearings. The southeast bearing angle is subtracted from 180 degrees to get the azimuth. The southwest bearing angle is added to 180 degrees to get the azimuth. The northwest bearing angle is subtracted from 360 degrees to obtain the azimuth. The angle of the northeast bearing is equal to the azimuth. The departures are calculated next. The sine of each azimuth is multiplied by the distance for the boundary to obtain the departure for the boundary. Each departure is placed in the appropriate cell in the column. The latitudes are calculated. The cosine of each azimuth is multiplied by the distance for the boundary to obtain the latitude for the boundary. Each latitude is placed in the appropriate cell in the column. Since the description comes back to the point of beginning, the sum of the departures and the sum of the latitudes should equal 0. In this case, they do not, but are far closer to 0 than often occurs with old descriptions. This step is often referred to as checking the closure of the description. This closure check is a task often performed in the analysis of descriptions. Obviously, if neighbors are fighting over less than a foot, it is hard for the surveyor to justify an opinion that would reject one position over another based on the description alone if the closure error is greater than 1 foot. Next, the second x and y coordinates are calculated. The first departure is added to the beginning x coordinate. The first latitude is added to the beginning y coordinate. The third x coordinates and y coordinates are calculated by adding the second departure to the second x coordinate and the second latitude to the second y coordinate. The fourth x and y coordinates are calculated by repeating the procedure. The procedure is repeated until coordinates for the starting point are calculated again. Ideally, the last coordinates calculated should be the same as the first coordinates. In this case, they would not, since the sum of the departures and the sum of the latitudes did not sum to 0. The same difference between the starting x-coordinate and ending x-coordinate should be the same as the sum of the departures. The difference between the starting y-coordinate and ending y-coordinate should be the same as the sum of the latitudes. Coordinate calculations are often part of traverse computations. A traverse is a series of angles and distances that should form a mathematically closed figure. A traverse is used to extend a control framework from which field information is integrated for analysis. From the traverse, so-called side shots are made to items the surveyor will wish to use in their analysis. Of course, the traverse could just as readily be employed by an engineer with side shot to items that must be located for a pre-engineering design, such as utilities, structures, boring locations, etc. In a traverse, angles and distances are measured. An example traverse is shown. This is a physically closed, geometrically closed traverse. In other words, the traverse starts and ends at the same point. A mathematically closed, geometrically closed traverse allows for several checks on field data and its capture. These checks will be explained. The first step is to enter the field information into the table. The field information consists of the interior angles and the distances. A direction is also included. The direction, in the form of an azimuth between traverse stations 100 and 101, is included. If the traverse had not been already drawn, the next step would be to sketch what the traverse looks like. The sketch aids in calculating the azimuths. The angles are summed. Had there not been any errors, the interior angles should sum to equal the number of stations or corners or sides of the traverse minus 2 times 180. Thus, the interior angles in a triangle with 3 corners or 3 sides would equal 180 degrees. The interior angles in a rectangle with 4 corners or 4 sides would equal 360 degrees. In the example, there are 5 stations. Accordingly, the interior angles should sum to be 540 degrees. The interior angles do not sum to 540 degrees. If the exterior angles were to be used rather than the interior angles, the sum of the exterior angles should equal the number of stations or corners plus 2 times 180. Thus, the interior angles of a triangle having 3 corners would equal 540 degrees. Next, the angles are adjusted so that the adjusted angles do equal the number of stations or sides minus 2 times 180 degrees. The difference between the sum of the angles and 540 degrees is obtained. This difference is divided by the number of angles to give the error, or conversely the correction, per angle. Some survey specifications will give a maximum tolerance for the errors in the angles. If the error per angle exceeds this tolerance, the angles in the traverse must be remeasured. In the example, if the sum of the angles is greater than 540 degrees, the correction would be subtracted. If the sum of the angles is less than 540 degrees, the correction should be added. The adjusted or corrected angles are found by adding the correction per angle. The corrected angles are summed to make sure that the corrections were correctly applied. The sum of the adjusted angles must equal 540 degrees or an error has been made in the adjustment. It is worth noting that sometimes a source of the error may be found or assumed to be confined to one angle, in which case the entire angular correction or most of the angular correction is made to that one angle rather than distributed to all the angles. The next step is to calculate the azimuths. The diagram may best illustrate how the azimuths are to be calculated. Beginning with the azimuth from 100 to 101, the reverse azimuth is found by adding or subtracting 180 degrees. The interior angle at station 101 is added to obtain the azimuth from station 101 to station 102. If the azimuth exceeds 360 degrees, then 360 degrees is subtracted from the azimuth. The azimuth from station 102 to 103 is calculated in the same fashion. The back azimuth from stations 102 to 101 is found by adding or subtracting 180 degrees. The interior angle at station 102 is added to obtain the azimuth from station 102 to station 103. The procedure should now be obvious. Calculate the back azimuth, add the interior angle to obtain the next azimuth. The procedure is repeated until the azimuth back to the point of beginning is found. The procedure is repeated one more time using the angle of the starting station. The azimuth calculated in the last step must be equal to the starting azimuth or an error has been made. Having calculated and checked the azimuths, the latitudes and departures are now calculated. The departures are calculated by multiplying the sine of the azimuth by the distance. The latitudes are calculated by multiplying the cosine of the azimuth by the distance. The latitudes and departures for each course are calculated. Since the traverse starts and ends at the same location, the sum of the departures should equal 0, and the sum of the latitude should equal 0. They do not. The linear error of closure is calculated from the error in the departure and latitude. The linear error of closure is the straight line distance between the ending point and the starting point. The linear distance that comprises the linear error of closure is calculated by squaring the error in departure and squaring the error in latitude. Adding the two squared values together and taking the square root of the sum results in the linear distance between the starting and ending points, or the linear error of closure. Of course, the linear error of closure does not give a perspective of the precision of the survey work. Was the linear error of closure the result of surveying around the boundaries of Alaska, or perhaps a small 1¼ acre lot? A 5-foot linear error of closure resulting from the survey of the boundaries of Alaska would be great surveying work, while a quarter of a foot linear area of closure around a 1/4 acre lot would be poor surveying work. Accordingly, the relative area of closure is calculated. The relative area of closure is determined by finding the ratio of the linear area of closure against the total distance of the traverse. The ratio is properly expressed as a factor of 1 to the distance. Accordingly, the linear area of closure is divided by itself to give the 1, and the total distance is divided by the linear area of closure to get the relative area of closure into a factor of 1 to some distance. The relative area of closure is often compared to minimum standards. If the traverse does not meet the standards, all or part of the survey must be redone. For small relative area of closure, no adjustment needs to be performed. For example, if the linear area of closure is 0.1 feet and a corner monument is a 16-inch diameter maple, the area in the traverse is lost within the size of the monument. Adjustment of the traverse can be done by using one of 3 common methods. The 3 common methods are least squares, compass rule, and transit rule. Least squares is the most statistically rigorous method, but not easily done without software. The method of least squares will be left to another lecture. The compass rule presumes that the errors are a function of the distance. In other words, the longer the distance, the greater the error. The compass rule probably had a sound basis when distances were taped. However, with the advent of electronic measurement of distances, there is little basis for using this method. Yet the compass rule is still popular. The ratio used for the correction for the departure is equal to the total correction of the departure divided by the total of the traverse distance. The total correction of the departure is merely the error in departure with the sign reversed. The ratio for the departures is then multiplied by the distance for each line to obtain the correction for the departure of that line. The correction is added to the departure of the line to obtain the adjusted departure for that line. Similarly, the ratio for the correction for the latitudes is equal to the total correction of the latitude divided by the total of the traverse distance. The total correction of latitude is the error in latitude with the sign reversed. The ratio for the latitudes is then multiplied by the distance for each line to obtain the correction for the latitude of the line. The correction to the latitude is added to the latitude of the line to obtain the adjusted latitude for that line. The adjusted departures must sum to 0, or there is an error in the adjustment calculations. The adjusted latitudes must sum to 0, or there is an error in the adjustment calculations. The transit rule uses a combination of the azimuths or angles and distances to form the basis for the adjustment. The transit rule requires the absolute value for each departure be summed and the absolute value for each latitude be summed. In other words, make all the departures positive and all the latitudes positive and sum the values. The ratio used for the correction for the departures is equal to the total correction of the departure divided by the total of the summed absolute values of each departure. The ratio for the departures is then multiplied by the absolute value for the departure line to obtain the correction for the departure of that line. The correction is added to the departure of the line, not the absolute value, but the actual departure of the line to obtain the adjusted departure for that line. The ratio used for the correction for the latitudes is equal to the total correction of latitudes divided by the total of the summed absolute values for each latitude. The ratio for the latitude is then multiplied by the absolute value for the latitude of the line to obtain the correction for the latitude of that line. The correction is added to the latitude of the line, not the absolute value for the latitude, but the actual latitude of the line to obtain the adjusted latitude. The adjusted departures must sum to 0, or there is an error in the adjustment calculations. The adjusted latitudes must sum to 0, or there is an error in the adjustment calculations. The next step is to calculate the coordinates. The equation for the x-coordinate is shown. Accordingly, the x-coordinate for station 101 is found by taking the x-coordinate for station 100 and adding the departure between station 100 to 101. Similarly, the x-coordinate for station 102 is found by taking the x-coordinate for station 101 and adding the departure between station 101 to 102. The process is repeated until the x-coordinate for 100 is calculated. This should be the same x-coordinate as the beginning. The equation for the y-coordinate is shown. The y-coordinate for station 101 is found by taking the y-coordinate for station 100 and adding the latitude between station 100 to 101. Similarly, the y-coordinate for station 102 is found by taking the y-coordinate for station 101 and adding the latitude between station 101 to 102. The process is repeated until the y-coordinate for 100 is calculated. This should be the same y-coordinate as the beginning. Once the traverse stations are calculated, the side shots are calculated. The first step to calculate side shots requires calculating the azimuth from the traverse station to the side shot. This step is accomplished by taking the azimuth from the traverse station to the backside station. From this azimuth, the angle to the side shot is either subtracted or added as required. The azimuth for the 3/4 inch pin from station 100 is found. The azimuth for the standing stone from station 101 is found. The azimuth for the 1-inch pipe from station 103 is found. Finally, the azimuth to the blaze tree from station 104 is found. The x-coordinate for the 3/4 inch pin is found by taking the x-coordinate from station 100 and adding the sine of the azimuth times the distance. The x-coordinate for the standing stone is found by taking the x-coordinate from station 101 and adding the sine of the azimuth times the distance. The x-coordinate for the 1-inch pipe is determined by taking the x-coordinate of station 103 and adding the sine of the azimuth times the distance. Finally, the x-coordinate for the blaze tree is calculated by taking the x-coordinate of 104 and adding the sine of the azimuth times the distance. The y-coordinate for the 3/4 inch pin is found by taking the y-coordinate from station 100 and adding the cosine of the azimuth times the distance. The y-coordinate for the standing stone is found by taking the y-coordinate from station 101 and adding the cosine of the azimuth times the distance. The y-coordinate for the 1-inch pipe is determined by taking the y-coordinate from station 103 and adding the cosine of the azimuth times the distance. Finally, the y-coordinate for the blaze tree is calculated by taking the y-coordinate of 104 and adding the cosine of the azimuth times the distance. More on this sample problem later. Before leaving traverse calculations, the situation of a physically open but geometrically closed traverse must be explained. A physically open but geometrically closed traverse does not loop back to the starting point, but does end on a known point with a known azimuth. Going to the previous example, another traverse has been run between station 101 to 104. A diagram illustrates where this traverse is located. The coordinates for station 101 and station 104 are known from the previous calculations and closed traverse. The angles and distance of the physically open and geometrically closed traverse are shown. There are two known azimuths. One azimuth is at the beginning of the traverse. The second azimuth is at the end of the traverse. The angles cannot be summed and compared to the equation of n-2 times 180 degrees. In order to calculate the error in the angles, the azimuths must be calculated. The azimuths are calculated by finding the reverse azimuth by adding or subtracting 180 degrees, then adding the clockwise angle. The final azimuth should equal the given or known final azimuth. If the final calculated azimuth does not equal the given final azimuth, The difference between the known azimuth and calculated azimuth is determined. The difference between the azimuth is divided by the number of angles in the open traverse, then subtracted or added depending on the direction of the error. The angles are adjusted by the correction. Revised azimuths are calculated using the adjusted angles. Next, the departures and latitudes are calculated using the adjusted azimuths and distances. The sine of the azimuth times the distance gives the departure. The cosine of the azimuth times the distance gives the latitude. The sum of the departures and the sum of the latitudes will no longer equal or sum to 0. For a geometrically closed, physically open traverse, the sum of the departures should equal the difference between the ending x-coordinate and the beginning x-coordinate. If the sum of the departures are not equal to the difference in the coordinates, the variance is the error in the departure. The sum of the latitude should equal the difference between the ending y-coordinate and the beginning y-coordinate. If the sum of the latitudes are not equal to the difference in the coordinates, the variance is the error in the latitude. At this point, the subsequent calculations are the same as the geometrically closed and physically closed traverse. The departures and latitudes are adjusted and the coordinates calculated.